parties with inputs x1 to xn. There is an adversary who corrupts at most t parties, where t is at most half of the parties, typically in this setting. And your goal is to compute some public function f without revealing anything more than the result of the function. Okay, so information theoretic computation has been well studied. And among the many things that are well known, we know that it's impossible to securely compute a function if you don't use randomness, right? Deterministic secure computation is not possible. You need the ability for the parties to toss cryptographically secure random coins. So a well-studied question is to understand how much randomness do we need to securely compute some arbitrary function f. And the motivation for that is that it's not always easy in the real world to produce high quality cryptographic randomness. You need to use a proper piece of code. You need to use a good randomness generation strategy. So it's natural to treat randomness as a scarce resource and to attempt to minimize how much of it we need. In this work, we ask a different but related question, which to our knowledge was never asked in the past. What we ask is, what is the minimum number of parties in a protocol that need to have the ability to toss coins in order to be able to evaluate an arbitrary function f? So the motivation for this related question is slightly similar. In the real world, our randomness generation abilities might differ. Some might be using a powerful server with a proper implementation of the cryptographic mechanism. And so this server might be able to produce reliably high quality randomness, and everyone might be okay trusting this randomness, but others might be using less trusted software or less powerful devices. And we might not want to trust their ability to generate high quality randomness throughout the protocol. So for example, in my example, we might want to ask the two parties that use their cell phone to participate to the protocol to not produce random coins during the protocol. We don't want to trust their ability to toss cryptographically secure random coins. So is it possible to run the protocol without having them tossing any coins? So that's the question we ask. And our main result is a complete characterization of what we call the random source complexity of T private computation, where T stands for the number of corrupted parties. So I'm giving you the picture here. What was known before was this result by Kushilevitz and Mensur from PODC 96, which shows that T parties need to have the ability to toss coins to be able to T privately compute some functions, and in particular the XOR function, where the parties want to obtain the XOR of all their inputs. So actually, at the time, Kushilevitz and Mensur wanted to prove a lower bound on the number of bits you need to toss to compute the XOR functionality, but sorry, actually their lower bound is proven by showing that you need at least T different parties to have the ability to toss random coins. So we observe that in particular, it extends to the stronger result that you need at least T sources for any function, for some simple functionality such as XOR. So that's our previous work. So we start with two relatively easy results. We show that you can actually slightly straighten the Kushilevitz and Mensur lower bound. For some randomized functionalities, you can show that you actually need T+1 parties with the ability to toss random coins. And furthermore, there is a matching upper bound showing that T+1 parties is sufficient to T privately compute any functionality. So in the sense, I call that the easy results because that's what makes sense, right? If the parties can corrupt up to T players, then if you have T+1 parties who can toss coins, you will always have one non-corrupted party who can toss randomness. So someone will produce randomness which cannot be corrupted. And if you do it the right way, you can use this randomness for everyone in the protocol. So that makes sense, and that's actually not too hard to prove. However, the really non-trivial and interesting result, which is our core result, is this one on the bottom left. We show that if we only look at deterministic functionalities, so which is still a huge class of functionalities, it actually suffices that T parties have the ability to toss coins to T privately compute any deterministic functionality. So I want to I want to let a minute to let this sink in, because it should be surprising. So what I'm saying is, we know that secure computation is impossible if the parties are deterministic, but here I'm claiming that secure computation for all deterministic functionalities becomes feasible, even in a world where the adversary could potentially corrupt all the parties who can toss random coins. So somehow it's possible to do secure computation with a randomness that could potentially be entirely seen by the adversary. And I don't know for you, but to me, it really sounds surprising at first sight. So that's for our first result. Okay. Yeah, so our second result is to try to understand a bit better the relation between the randomness complexity and the random source complexity. So in particular, if you want to use a minimal amount of random sources, can you do it while using not too much randomness, or do you need to blow up the amount of randomness you need to use? Okay. So it's typically very, very hard to prove randomness lower bounds in cryptography, and in general, tight lower bounds have only been proven for very simple functionalities. So as is the standard in the literature, we focus on some very simple functionalities. XOR has been handled by Kushilevich and Mansour. So we look into the end functionality, and we look at the simplest case of one privacy. And even in this very simple case, we don't have tight upper and lower bounds. It's a hard problem. It has been looked at a few times in the past. So currently, the best known protocol for one private n-party end is a TCC 19 paper that securely compute the n-party end using 8 bits of randomness and 2 sources. So we ask, well, if you want to use a minimum number of sources, which by our previous result is 1, is it possible to match this lower bound? And surprisingly, we actually managed to improve simultaneously the randomness complexity of the protocol. We lower it to 6 bits and to use a single source. So it's a result which is also of independent interest as a study of randomness complexity for some simple functionalities. So as a starting point, as a warm-up, I'll explain why if you have T+1 sources, you can T privately compute all functionalities, which is a result that you should expect to hold. And then I'll devote most of the presentation to our core result, and the fact that if for deterministic functionalities, actually T parties tossing coins are necessary. If you want to see the lower bound, I encourage you to see the paper. So assume you have T+1 sources. So here I take 5 parties. I assume that T is 2. So we have a honest majority. And so we have 3 parties who can toss random coins, depicted here with those little coins. And we want to compute some function f. Okay. So the ID is just to let all the parties which can toss random coins, we just want to let them all send a random tape to each party who cannot toss random coins, right? So my party here will send a random tape to the 2 parties here who cannot toss random coins. And so we'll do everyone with the ability to toss coins. And in the end, all the parties who did not have a random tape set their random tape to the XOR of all random tape you received from all parties who can toss coins. And of course, afterwards, with all these random tapes, they can run any information theoretic secure computation they like, for example, BGW. And this works fine because since there are T+1 sources, there will always be an uncorrupted source. So when you XOR the random tapes from the viewpoint of the adversary, these random tapes will be truly random. So we can just invoke the security, for example, of BGW, right? So that's simple. Now, how do we do if we actually want to have only T sources? So now I go back to the setting of computing F, but I want to compute a deterministic function. And I only have 2 parties who can toss random coins. And here, I have to deal with the fact that the adversary could potentially corrupt all the sources, in which case he will see all the randomness ever used in the protocol. So if I want to defend against that, I have to isolate the sources. In a sense, I have to shield the adversary from seeing things that these sources could see throughout the protocol. So we put the sources aside, right? And because we don't want them to participate to the protocol, we will let them share their inputs between the deterministic parties, so that the deterministic parties will have all the information necessary to compute everything without using the sources, which we want to keep isolated. So the two sources share their inputs, and then the three deterministic parties here will replace the initial functionality by a new functionality f prime that will first reconstruct the shared inputs of the sources, and then apply the function f on the reconstructed input plus the joint inputs of the deterministic parties. So what you would expect. Now, our three parties need to be able to compute the function, and they will do so using GMW. So a very important thing to know is to observe is that now that we've isolated the sources, here there might be there might not be a honest majority anymore among those guys, but among those deterministic parties, we know that there will always be at least one uncorrupted party. So we use a protocol like GMW that can tolerate up to n-1 corruptions out of n. So what's GMW? It's a well-known secure computation protocol that allows you to securely compute any Boolean circuit. And I'm skipping a few details, but the core thing here is that the parties maintain as invariant the fact that they have shares of the computation through the wires of the circuit. Computing XOR gates only involve local computation, and computing AND gates can be done by consuming what's called the Beaver triple. So this is combining the standard GMW protocol with the well-known observation of Beaver. So none of this uses any randomness, except the part where we want to compute an AND gate, which is done by consuming a Beaver triple. So what we use is we use an inner protocol, which will of course use the sources because that they are the one who can produce randomness to compute those Beaver triples. So whenever we want to compute the Beaver triples, we invoke this inner protocol where first the source will send random tapes to the deterministic parties. So as in my warm-up example, the parties XOR the tapes in order to have their own random tape. And then all parties together run a distributed BGW protocol where everyone, for the randomized functionality, that outputs random Beaver triples only to the three deterministic parties here. So that's exactly like our warm-up protocol, the T+1 source protocol. But the crucial thing is that now I'm only applying this protocol in a safe context because this functionality here is independent of the inputs. So even in a world where the two sources will be corrupted, nothing too bad can happen because nothing in this protocol will ever depend on the private inputs. Okay. So the deterministic parties use GMW. They do everything among themselves, but whenever they need a Beaver triple, they go back to the sources, they run a BGW protocol all together, and at the end of this BGW protocol, they get a Beaver triple, and they can use this Beaver triple in GMW. They do that until they get the output, and then they send the output back to the sources. Why is this secure? There are two cases to study. The first one is the case where at least one of the sources is honest, and the second is the case where no sources are honest, in which case we know that the adversary did corrupt all the sources, but also only the sources. So for the first case, two observations. If there is one honest source, then in this third phase of the protocol here, we know that the BGW protocol was secure because the adversary cannot control all sources. So the shared tapes are truly random. So we can invoke the security of BGW. So the Beaver triples, we can think of the Beaver triple used in the GMW protocol as coming from a trusted source of Beaver triples. And also we know, since there is a honest majority of parties, because T is below n/2, that there will be at least one honest party. So we can invoke the security of GMW in the outer protocol, and security follows. In the other setting, where the adversary will corrupt all sources, then we know that the adversary corrupts only the sources. And in this case, we simply observe that no source ever sees anything dangerous, right? In the input sharing phase, only the source communicate to the players. In the outer protocol, the sources are never involved. In the tape sharing phase, only the sources communicate to the players. And the BGW protocol, as I said, is input independent. So here, nothing bad can happen. The only thing they get is the output in the end. That was for security. Now in the 5 or 4 minutes that I have left, maybe 3 minutes, I want to talk a bit about the second result. So one private N party end with 6 bits and 1 source. So the motivation is that N is a basic building block of MPC. And for the other basic building block, which is XOR, we already have tight lower bounds. The randomness complexity of one private end has been studied in previous works, and we know that you can do it with 8 bits and 2 sources. So that's our setting. Parties have a single bit each, and they want to compute the end of all their bits. So we have a budget of 6 random bits. And the way we do it is we'll have P0 toss all random coins throughout the protocol. The parties will communicate in a line where P0 will communicate with P1 and P2, P1 will communicate with P2 and P3, and so on. And we'll proceed as follows. The protocol starts by having P0 share X0 and X0 times some mask, which is a random mask that it produces. So producing the mask and sharing X0 and X0 times the mask, that uses already 3 random bits. And those 2 things here, they will be our invariant throughout the protocol. Meaning that the parties will always have shares of the products of all xi's so far, and the product of all xi's so far times a mask. So now we just have P0 send the right-hand side of the shares to P1 and the left-hand side of the shares to P2. So now P1 and P2 have the shares of this invariant, and he also sends the mask to P1. And we have P1 mask his input X1 using the mask. So that's why we call it the mask, and send this to P2. And the 2 parties do this local computation. So they do some kind of linear combination with this new mask. This is what that masks X1 and the shares that they have. And trust me on that, if you write the calculation, you can see that those 2 things here, they form additive shares of X0, X1 and X0, X1 times a new mask. So we successfully managed to maintain this invariant because now the parties P1 and P2 have shares of the product of the xi's and the product of the xi's times a masks, where we only added the new xi, like the x1, to this invariant. However, what goes wrong is that the first here is perfectly fine, but the second one is biased because it was computed by doing a local product of values. So the shares are not uniformly random, they are biased towards 0. So to randomize them, we let P0 sample an additional randomizer bit, which uses 1 more random coin from our budget. And we let P1 and P2 use this random bit to randomize this share. And if you do all of that, you notice that that one of the shares, this one here, was never used. I mean, its randomness was never used anymore. So we can reuse it, recycle it to define it as the next randomizer bit so as to maintain the invariant. So that's how we propagate the share, we propagate everything throughout the protocol until the end. In the end, what's left to do is just multiplying the last input of the last party to this product. And if you look closely at what we want to do exactly, what we want to do is exactly do an oblivious transfer, actually. And we know that oblivious transfer can be done with 3 random bits. So we could do that. And we actually also observed that the last randomizer bit is never used anymore, so we can recycle it for the oblivious transfer. Hence, we do the full oblivious transfer only using 2 additional random bits. And this way, all parties get the output. Yeah, so that's the end of my talk, and I'll be happy to answer any question.
Questions? Okay, so I have a couple of questions. Yeah, the last result that you showed was pretty interesting. The trade-off between the number of sources and the amount of randomness that you need. I'm curious if you can say anything more general other than this specific case of one private and N party.
So so more general, yeah. So we actually do have a conjecture in the paper. I did not mention it in the talk because it's only this, meaning it's a pure conjecture based on, say, a somewhat educated guess, because we tried to do the best we can and we don't see an obvious reason why we should be able to do better. So let me tell you what's a conjecture. What I will conjecture, but I'm not 100% sure that my co-author will conjecture exactly the same thing, but what was stated in the paper seems to work, is that if you want to use a minimum number of sources, which is T sources, then you need a factor T blow up in the randomness complexity. Meaning, if you take any non-trivial functionality, so sufficiently non-trivial functionality, so for example, something that will involve multiplication gates and the like, so not just a simple linear functionality, and you call R the best randomness complexity that you could possibly achieve in a world where everyone can toss random coins, then if you only want the minimum number T of parties to toss random coins, you will need an amount of randomness proportional to T times R to securely compute it. And we know that T times R can be achieved because this is what our protocol achieves, the one for T sources for all deterministic functionalities. And we conjecture that it's the best you can do. And that here, that means that in the setting of 1 privacy, we're expecting to be able to match actually the best possible randomness lower bounds, because the factor T is just a factor 1.
Interesting. Thanks. That's pretty cool. Also, I was wondering if you considered a model. So if I understand correctly, in this model, you sort of know ahead of time which parties are not going to be random sources and which ones are. So
yeah.
Yeah, I was wondering if you could say something about a model in which you don't know who's going to have bad randomness and so on.
Yeah, so if you have no idea, it's a very natural question. If you don't know in advance who could have bad randomness, actually, I don't think, I'm pretty sure we can't say anything better than the easy results, meaning there is no way to do this strategy of isolating the sources. So isolating the sources is also separating the people who could have bad randomness and making them compute the function on a side. And if you can't do that, then there is nothing non-trivial you can do. Meaning those upper bounds with T plus 1, they also hold if you don't know in advance who can toss random coins, right? So you will also have the ability to compute any functionality with T plus 1 random source just by using this warmer protocol where everyone will share, all parties, there you would ask all parties to share random tapes with everyone, and then everyone will define his own random tape to be the XOR of all random tapes received by all parties. This way, if at least T plus 1 sources can produce high quality randomness, then you will have re-randomized properly all random tapes of everyone, and that's the best you can do. You cannot hope for better if you don't know who are the parties with the low quality randomness. So yeah, it's a setting where you can't say much. The setting that we consider is also well motivated by the fact that in the real world, you might have a good idea of who's using a trusted device and who's using, I don't know, his cell phone.
Much. Thanks for the talk. Okay. So the next talk will again be given by Shofra. It's going to be on non-interactive secure computation of inner products from LPN and LWE. This is joint work between Shofra Koto and Mariam Zarezadeh.
So hi again, everyone. I'm following directly with a second talk. So as was said in the introduction, it's a joint work with Mariam Zarezadeh, and I'll be talking about non-interactive secure computation of inner products from LPN and LWE. So, so let me start by recalling briefly non-interactive key exchange. Non-interactive key exchange, you all know what it is. It's a protocol where n parties will simultaneously broadcast their public key. I'm looking only at like non-interactive key exchange between pairs of parties. So, and so n parties will simultaneously broadcast a single message. And then after broadcasting their single public key, any pair of party without further interaction can locally compute from its state and the other party public key their shared key. right? So you can do it here between P1 and P4, but you can also do it between any other pairs of parties. And this is a very appealing interaction pattern. You use really only one round of broadcast, which is nice. And also you avoid the n² cost that you would have if you are using naive pairwise exchange. So you're shaving a quadratic amount of communication compared to non-interactive solutions. So a natural question is to wonder, would it be possible to obtain a similar appealing interaction pattern for some simple MPC functionality that go beyond simply doing key exchange? So here what I would want would be to have n parties who broadcast an encoding of their input, and then any pair of parties could securely locally compute without any further interaction their output from their pairwise output, right? So for some pre-specified function, fi of xiaj and fj of xiaj. And again, if you could do that, then you would have this nice feature of avoiding the n² overhead of having each pair of parties securely compute the function. And in this work, we show that it's possible to do non-interactive secure computation for shares of inner products between vectors held by the parties. So where now the functions fi and fj will form additive shares of the inner product between xi and xj over any field f of your choice. And so this is quite appealing because even if you want to securely compute the inner product in the end, then you don't have to send something whose lengths depend on the vectors xi and aj anymore. You only have to send a single element of f to reconstruct the output. So really it's one round of broadcast, you avoid the n² overhead on the big inputs, and then if you want to reconstruct the output, you just need to send a single field element. So why non-interactive inner products beyond the fact that we can do it? Well, it has many natural applications. It's a simple but super useful function. I'm listing a few here: biometric authentication, pattern matching, and many more. Just as a quick example, let's look into what you could do for biometric authentication. So it's known that inner product and Hamming distance, that's basically the same thing, right? You can locally reduce Hamming distance to the computation of an inner product. So that suffices for computing Hamming distance between strings. So you could imagine that you have n clients and m servers, each with their fingerprint stored. And ahead of time, each party will publish an encoding of its fingerprint, right? So the clients will send their own fingerprint and the server will send the fingerprints that are stored. And afterwards, after this single round of publishing and encoding online, any client and server pair can locally compute additive shares of the Hamming distance between the two fingerprints. And afterwards, to authenticate to the server, the client only now has to send a single field element, which is his share of the Hamming distance, from which the server can check whether by reconstructing the Hamming distance is below the threshold or not, and allow for the authentication. So, and that's quite appealing interaction pattern in a setting where you will do like biometric authentication between multiple clients and multiple servers with a minimal interaction pattern and a low communication. So how do we do that? We'll use LPN and LWE. So I'm briefly recalling the assumptions in a somewhat semi-abstract way. So what I call the primal form of LPN and LWE is the following. You have some random matrix, and you have some noisy system of linear equations. And the assumption will be that this noisy system of linear equations is indistinguishable from random. Now, if you set, for example, random matrix to be random over F2, and you set the short secret to be also over F2, and the noise to be sampled from a Bernoulli distribution, meaning that it will have mostly zero entries and a few non-zero entries, then you get the LPN assumption, and you can actually define natural variants of LPN over FP, where everything's over FP, and now the noise is from a Bernoulli distribution over FP. So mostly zeros, but a few random field elements here and there. So that's what I'll call LPN, where the noise is sparse, and you recover LWE by setting the noise to have small magnitude instead. I'm here giving the example of picking the noise uniformly between some bounds, but of course, many other distributions are standard. And I said primal form because you can also consider a dual form for LPN and LWE. In coding CRT terms, you can view G as a generator matrix of some linear code, and you can multiply it on the left by its parity check matrix, which will cancel the matrix, and then you'll be only left with some kind of random but now compressive matrix H. And your assumption is that if you multiply this compressive matrix H by a noise, which can be sparse for LPN or short for LWE, then you get something that looks random. And actually, I mean, this is really for the sake of being abstract, because in the case of LWE, generally this will be an information theoretically secure result by the leftover hash lemma. But for LPN, this will be an assumption which is equivalent to LPN. Okay, so our starting point is Alekhnovich key exchange. So what I promise is that we want to do non-interactive key exchange. I mean, we want to do secure computation as easy as non-interactive key exchange. So we start from a non-interactive key exchange, and we look at Alekhnovich, which is a celebrated key exchange from LPN. Here, Alice and Bob will both compute public keys. Bob will do that as some dual LPN sample, and Alice will compute it as some primal LPN sample, using the primal form and the dual form. Okay, so let me show you how correctness works. We just compute the keys K and K prime by just doing the inner product between the public key and the random, the sparse random vectors locally kept by the parties. And to look at correctness, we just open everything. And so if you open everything, what you get is just exactly the key of Alice here, plus some inner product between two sparse vectors. And because this is sparse, you can just view that as a noise term, because this inner product will be 0 with high probability. So roughly, if those two things here have Hamming weight T, and this thing is of size N, then the probability is that this noise term is 1 is roughly T squared over N, which for a sufficiently large N and a sufficiently small T is much smaller than 1. So that's Alekhnovich key exchange. Of course, if you want perfect correctness afterwards, you need to do some reconciliation protocol to amplify the correctness of your output key, but that's a high-level idea. So for security, we invoke the dual LPN assumption, which is equivalent to LPN on Bob's side, and the primal LPN assumption on Alice's side. Proof is standard, I'm skipping it. So now our core question is the following. We know that in order to compute their keys, the parties are already computing an inner product. So could we somehow use the fact that we have already this nice inner product computation that's taking place in Alekhnovich key exchange to embed a more complex functionality inside our key exchange? Could we possibly embed the computation of an inner product inside Alekhnovich key exchange? So let's do a warm-up attempt. Bob can have some vector of input and can just add it to his public key, right? So now if we again open the computation, we open everything, and we have the same thing as before, except that now we have this S times X term here, and I added a minus sign for simplicity. So now if you add Alice and Bob's results, the K terms cancel, you have this noise term, and you have this inner product here. So now K and K prime form noisy additive shares of the inner product between X and S. So this is getting somewhere, but this is still not an inner product because this S here is not something that can be Alice's input, because it has to be truly random if you want to ever invoke the security of LPN. So you can't use S as the input of Alice. So how do we embed Alice's input inside this S? Well, the second idea is just to split H vertically as the vertical concatenation of two matrices H0 and H1. Here, the idea is the following. If you write it this way, then when you open the computation, you can simply use the randomness inside S0 to prove that everything here is secure, is indistinguishable from random, because you will have a term H0 times S0 plus R1, which is a primal form LPN sample. So you can invoke LPN at the cost of losing a factor 2 in the rate of your code here. And now this other part here is a part where you can put something. And this something does not need to be random anymore. So you can decide that it will be the input of Alice. And then when you open the entire computation here, you actually have this S0 term here, but just by padding Bob's input with zeros on the top, then you can cancel the part that involves S0. And so now you just get some noisy additive shares of the inner product between X and Y, so the inputs of Alice and Bob. And so that's for the LPN-based protocol. It's a protocol that gives you non-interactive inner products with some inverse polynomial noise that you can make as small as you want by increasing, for large enough vectors. What about efficiency? Well, communication-wise, if you pick standard parameters, you'll have something like 2 mbits from Bob and 4 mbits from Alice with reasonable parameters. So just exchanging the inputs in the clear will be 2 mbits of communication. Here we're around 6 mbits of communication. So just a factor of 3 overhead over just exchanging the inputs in the clear. And asymptotically, when the size m goes to infinity, it actually suffices to send 1 plus epsilon m bits from each party, and you get nearly optimal communication overhead for this inner product protocol. So that's quite good. And in computation, the cost is of course dominated by the big matrix multiplication. If you take standard variants of LPN, such as LPN using quasi-cyclic codes, it's a standard variant that has been used in a bunch of NIST submissions and many other works, then you get quasi-linear computation in M. And using some slightly more exotic variants of LPN, such as LPN for Drake-Ishai codes, you can actually make it strictly linear in M. So actually strictly linear computation, which is also a nice feature that's not easy to have with other protocols. And security is exactly as in Alekhnovich key exchange. So that's good, but the protocol has t²/n correctness error. And now if we go back to for example, our example of biometric authentication, if you want to use this protocol in an n-party setting, this correctness error will actually translate to a security error because each time an error occurs, then the server that sees the error will learn a linear equation of the form v times r, where v is a non-vector and r is the noise vector. So the server will, for each error, accumulate one linear equation about the noise. So if many servers were to join their forces, they could accumulate many linear equations about the noise. As long as the number of servers is not too big, so you won't have too many errors overall, then this is still a secure protocol, but the security now only holds under some variant of LPN, which is an LPN with leakage assumption, and this variant can be reduced to a standard LPN assumption, but there is a loss. Alternatively, if you might have a large number of errors, or if you don't want a correctness error, for example, for biometric authentication, maybe you don't want a failure with a 1% probability, then we give two alternatives: either an LWE-based protocol that directly achieves negligible error probability at the cost of more communication, or a way to remove errors via a sublinear preprocessing phase. So I'm going to describe both alternatives. So, let me just state also that, so this preprocessing phase adds more interaction. So it's not fully non-interactive anymore, but it's independent of the inputs. So this interaction only takes place ahead of time. And the amount of communication and computation there is also logarithmic in the input side. So it's a very small amount of communication and computation to the preprocessing. And then everything is local work in the online non-interactive phase. So it's still quite interesting. So we start again from this Alekhnovich-based inner product protocol, and we convert it to be an LWE-based protocol. So we now have X over ZP. The matrix is over some field ZQ, some ring ZQ, and we scale the X and Y by Q over P. And now when you open up everything, you have the same thing as before, except that this thing here has been scaled by a Q over P. Actually, probably only one of them should have been scaled, whatever. So now what you have is additive shares of some inner product scaled by some factor plus some noise term. And now this noise term is small in magnitude because it was computed as the inner product between two noise terms, which are small in magnitude. And we can invoke at this stage a well-known lemma from which is called the rounding lemma, which states that if Q is sufficiently larger than P and the noise magnitude, then the parties can just locally round their noisy shares of the inner product and directly recover additive shares of the inner product without any noise, with overwhelming probability and without using any additional communication. So the bonus is that by doing so, you achieve directly negligible correctness or N leakage while staying fully non-interactive. One run on broadcast, and then you get those additive shares of inner product. The downside is that you get to use a larger communication overhead because you need Q to be sufficiently larger than P and the noise bound. So that's for the LWA-based protocol. As for preprocessing, the key idea is, so back to LPN, the key idea is that we want to use preprocessing to pre-sample the sparse vectors R0 and R1 together with shares of these sparse vectors. So that later when we do the online phase, if you look at the noise term is the inner product between R0 and R1. So if the parties already have additive shares of R0 and R1, by adding these additive shares to their output, they can just cancel this noise and obtain noise-free output. So the only thing they need is, prior to executing the online phase, to obtain via this preprocessing functionality shares of two sparse vectors together with the corresponding sparse vectors. And the cool thing about that is that if you just open what a sparse vector is, this can be done with very low communication. So if you just write a sparse vector as a sum of unit vector and you open everything, you get that this inner product can be written as a big sum of products between coordinates multiplied by something which is 0 or 1, depending on whether the coordinates are at the same position. And this can be securely computed using some simple secure computation, using a bunch of equality tests to test equality with the positions and obvious linear evaluation for these products. So overall, you can compute this functionality using only t² times log n communication when the size of the things are proportional to n. So you gain an exponential factor compared to doing things naively. And actually, if you use a variant of LPN, which is also a standard variant of LPN used in many previous work, which is LPN with regular noise, where the noise is broken in blocks with a noisy coordinate in each block, then you can further bring the cost down to t times log n. So you can shave an additional factor of t and get a truly low communication for this preprocessing. And the last thing I wanted to briefly mention is that we also looked at malicious security. And if you break things down the right way, the thing we would need for malicious security will be to have the ability to prove that Alice and Bob correctly generated their public keys. So we want a zero knowledge proof of knowledge of some sparse vectors that satisfy some appropriate linear equation. And we do introduce a new efficient zero knowledge proof of knowledge for such LPN relation, which has communication which is exponentially smaller than the dimension of the LPN instance, because it's only proportional to t times log n, where t is the amount of noise and n is the dimension of the LPN instance. And so, whoops. And the key idea here is that we build on recent work on pseudo-random correlation generators, which showed that it's possible to generate with very low communication additive shares of things of the form delta times r, where delta is an element of an extension field and r is some random sparse vector. So we use a protocol like that to share a delta times r protocol using a function secret sharing, which can be done very efficiently using a length doubling to the random generator. So it exists assuming any one-way function. And then we can use just standard secure computation technique like speeds-like technique to view this as a MAC authentication of the noise vector R. So now delta is an information theoretic MAC that authenticates the noise vector, and we can use this MAC to check the correctness of the computation of the public keys. And overall, we only used some logarithmic communication. And that's all for my talk. I'll be happy to answer any question.
Are there questions? Okay, I have a quick question. I mean, maybe this is just superficial, but it seems like this non-interactive secure computation paradigm looks a bit like this, like public key PCF type thing. I'm curious if there's any connection there, or if there are other ways to solve the same problem.
Yeah, so public key PCF for the audience will be that everyone will broadcast their public key, and then parties can, so for example, two parties will broadcast their public key, and then the two parties can then locally compute long pseudo-random correlated randomness. So the question can go in two directions. So first, can you use PCFs, public key PCF, to do non-interactive Key exchange, that's actually a good question, and I'm not so sure, because you would first need to generate the correlated. So you would use the PCF to generate shares of a random inner product in the first round, and then you will need the second round of interaction to de-randomize these random shares of inner product and to get really real shares of your input vectors. So that naturally that would be 2 rounds. Maybe there is a clever way to do it in 1 round. I'm not sure. What's sure is that the best known construction of public key PCF so far is they are considerably less efficient than what we can do here. The other way is whether we could see this actually as some kind of pseudo-random correlation generator or a PCF, and actually it doesn't seem so. I tried a bit to see whether I could view it as a way to generate some inner product correlated randomness, but that would not be a good way to generate inner product correlated randomness because it has communication linear in the size of the vectors, right? So the magic of a PCF is that the communication is almost independent of the size of the correlated randomness that you will share between the parties. If we're using our protocol to generate inner product correlated randomness, the communication will be linear in the size of the vectors, which will be much less appealing than having communication, say, logarithmic in the size of the vector, which is what you will get with PCF. So really what we gain here is not some kind of PCF-like advantage of being sublinear, but it's really the fact that we can directly, without any further interaction, compute an inner product between true inputs. So not an inner product between pseudo-random inputs. So the two are not directly comparable, I would say. Even though, yeah, we used fairly similar IDs and techniques, right? Using LPN inside MPC, using some kind of function secret sharing in the end to handle malicious behavior. It really comes from the same set of techniques and IDs, but the results are somewhat incomparable.
I see. Thanks a lot for the answer and for the talks. Thank the speaker again. All right, so now we have our next talk, which is Efficient Adaptively Secure Byzantine Agreement for Long Messages. This is a joint work between Ame Bhangle, Chenda Liuzhang, Julian Loss, and Karthik Nayak. And Karthik will give the talk.
Are you guys able to hear me?
Yes.
All right. Thank you so much, Yashwant, for the introduction. I'm very happy to be here. So today I'll be talking about our work on communication complexity of Byzantine agreement under adaptive adversaries. This joint work with Amay, Chenda, and Julian. So this work actually follows a rich line of work. So I'll spend the first 30% of my time trying to explain some of these prior ideas because it's all actually very helpful to know these ideas because they are used in our work as well. So the problem that we are talking about is Byzantine agreement. And the core idea is for n generals or n parties to agree on some value, agree on a battle plan in this example. So at the end of it, you want all of these Byzantine generals who are surrounding a castle to either attack or to retreat. And you want to do this even if some of these parties or some of these generals can be malicious or what we call as Byzantine over here. So up to T of them can be Byzantine, and yet you want the rest of them to agree on one of these actions. So said as different properties, you need 3 properties to hold. The first one is agreement, which says that no two honest generals should disagree. Second is validity, which says that if all generals start off with the same value, let's say all of them want to attack, then you actually output that value, that is, you actually attack. And finally, you want termination, which means that all of these parties eventually take one of these 2 actions. So Byzantine agreement actually finds applications in modern day blockchains. And with modern day blockchains, you have a large number of parties trying to achieve consensus among them. So one of the key properties that you're looking for is to reduce the amount of communication or the number of messages that are sent by honest parties, or the communication complexity of the entire protocol. Moreover, the parties who speak typically hold some position of power. So if an adaptive adversary can actually corrupt some of these parties, then potentially they can hurt the agreement validity or termination properties of the overall protocol. So what you would want in such protocols is for you to have security under adaptive adversaries. There may be other properties that you're also looking for example, better latency, dynamic availability, and so on and so forth. But for the context of this talk and with respect to this work, we are primarily concerned with these two properties on communication complexity and adaptive adversary. And very coarsely speaking, the goal that we want to achieve is the following. The question we are asking is the following. Can we achieve a protocol, a BA protocol, with low communication complexity while still being secure under an adaptive adversary? Okay, so I'll qualify what I mean by low communication complexity in the next few slides. So as far as communication complexity is concerned, even 40 years ago, there was a very strong statement made by Dolev and Rashik, who said that, any deterministic BA protocol needs honest parties to send at least T-squared messages. Over here, T is the number of Byzantine parties, which typically is of the order of n. So you're expecting communication complexity to be order n squared. And they basically showed that if fewer messages are sent, then there exists some honest party who would receive no messages. And at that point, you would have a safety violation. So does this mean we cannot do better? Turns out we can. And the keyword that we're looking for over here is deterministic. So the bound applies for deterministic protocols. If we use randomization instead, we can actually have a protocol with subquadratic number of messages. So how do we go about doing something like this? The key idea behind achieving a protocol with subquadratic messages is the following. So you basically elect randomly a committee of some size kappa. So let's say your original population is size n, this entire grid of parties where each dot represents a party. You elect a small committee of size kappa, and so if you have a minority corruption in the overall population, even after you elect, except for some slack, you will still have a minority corruption in the overall committee. So if I'm glossing over some of the slack parameters over here, but the minority corruption would translate to the committee as well. So at that point, what you can do is just require these parties in the committee to send messages to everyone else, and they would actually run the agreement protocol for you. And eventually, you'll have only communication between you'll only have kappa parties sending messages to all n parties, and the overall communication complexity that can then be bounded by n poly kappa. The reason why you have a poly over here is because of the number of rounds of communication, which may be kappa or poly kappa in such protocols. Well, what if you have an adaptive adversary? Note that kappa, which you're thinking of as a security parameter, is typically much smaller than n or much smaller than t. So an adaptive adversary actually has the capability of corrupting the entire committee. How do we address this concern? There was this very, very nice solution by Chen and Mikali in their work on Algorand, where they introduced this property called player replaceability, where they said, instead of having one fixed static committee, let's keep changing this committee after every round. So in a given round R among n parties, you can have a committee of size kappa. These committee members would send messages to everyone, all the parties. And in the next round, the role of these parties would be played by a different set of parties. So the committee would be replaced and hence player replaceable to a different set of parties. So in R+1, you'll have a new committee who would be sending messages to everyone, and you would keep electing newer and newer committees each time. So if you're thinking of this from the perspective of communication complexity, you still have kappa parties sending messages to all n people. So you still have n poly kappa communication. The advantage here, though, is that if the adversary does not know who to corrupt or who is going to speak at any given round before the round starts or before these parties speak, then you can use this to your advantage. So in particular, if parties in round R, the committee members in round R speak and they would send all of these messages, then even if an adversary actually corrupts these parties subsequently, these parties are no longer useful from the adversary standpoint, because in the next round, someone else is going to speak and someone else is going to hold this position of power. And if the adversary does not know who is going to speak in round R+1, then you have security under adaptive adversary. So what you do need, though, is for parties to know that they can self-select themselves and they can prove to the world that they are indeed in the committee. And it turns out that you can actually achieve this using verifiable random functions. Well, now we do have an adaptively secure BA protocol with order n polycapa messages, right? So are we done? Well, it turns out we are not. I still have about 10 minutes to speak in this talk. So what else can go wrong over here? Well, let's think about the size of your input value to begin with. So if we have an L-bit input, so we have n polycapa number of messages, but if we have an L-bit input, the communication complexity trivially would be NL polycapa bits. What happens if this L is, your input size is large, for example, L is omega n squared, or if you're thinking of it in a blockchain sense, your L is your block size, and if it is a large block, 10 megabyte size block, then this multiplicative overhead of n times polycapa can actually be very large. So this is actually addressed in a different line of work called BA extension protocols, where you're trying to split the agreement of the block with the size of the message itself. So you're trying to express Byzantine agreement of a large message as a function of Byzantine agreement for small messages. So the key intuition over here is to break the problem in 2 steps. One, you agree on a kappa bit accumulator value corresponding to one of the inputs. And this typically, using a standard Byzantine agreement protocol, the state of the art would require kappa n squared communication. And second, you would share the L-bit value separately using erasure coding techniques. So you need to ensure that the L-bit value that you're sharing, corresponds to the kappa bit accumulator value that you're agreeing upon. And these details I'm glossing over here. But then the key idea is you want to share this L-bit value efficiently because L can be large. How do you go about doing that? So note that erasure coding techniques allow you to split a message into smaller chunks in such a way that even if you receive some subset of these chunks, for example, a majority of the chunks or some parameter value that you set, so if you receive sufficiently many chunks, you can reconstruct this message. So a sender can just create sufficiently many chunks, let's say n different shares of these messages, S1 to Sn, each of size order L over n. And these parties in a separate step, in the next step, let's call it a reshare step, can share this message with everyone else. Okay, so at the end of the reshare step, if you're thinking of a party, so far as it receives sufficiently many shares, it can reconstruct this value. And note that, even if some parties are Byzantine and they do not share this value, it is okay, because you do not need all of the shares to reconstruct. So how much communication do we need in such a protocol? So if you're thinking of the distribute phase, the first phase over here, each party is sharing with n different parties a message of size L over n. So the communication is order L, but n different parties can actually be running the distribute phase in parallel. So your communication is ln bits. In the reshare phase, you're engaging in an all-to-all communication. And the message that you're sharing is of size L over n. So the total communication that you're incurring is ln. And you're also incurring a kappa n squared communication for agreeing on the accumulator value. So the total communication that you have is ln plus kappa n squared bits. So note that the first term over here is optimal, because if you're sharing an L-bit message with n different parties, you have to incur a communication of at least ln. So what you're trying to improve upon is the second term over here. So what have we learned? So here's what the state of the art looks like. So on the one hand, you have subquadratic communication complexity protocols under adaptive adversaries, which require sending ln polycapa bits. So this is not optimal when L is very large. On the other hand, we have BA extension protocols specifically designed for long messages, right? So the communication complexity is ln plus kappa n squared bits. And when L is very large, actually the kappa n squared actually gets folded into ln. But when L is large, but not that large, this is not optimal. So the natural question is, well, can we get the best of both worlds? That is, can we have a BA protocol with the communication complexity of ln poly kappa n bits, while still being secure under an adaptive adversary. So the ln term is optimal over here, and the second term over here is the best you can get as of now. So in the next sequence of slides, I'll present a high-level idea of how we actually achieve this. And I think what we learned until now would be very useful in understanding what we're trying to do. So we'll start off with using the BA extension protocol line of work as the baseline way of thinking. So we'll still break down the problem into two steps. The first part, agreeing on kappa bit accumulator value. Now, instead of using a protocol with kappa and squared communication, we can use a Chen-Mikali-like protocol, which would require order poly kappa and communication. So that's easy. The concern is, how will you share this L bit value, L bit input with all parties using erasure coding? Observe that with the approach earlier, if we concentrate on, let's say we concentrate on the reshare step. So reshare step requires an all-to-all communication. And even if each of these parties send at least one bit value, then the total communication incurred is omega n squared. And that's too high for us. We want everything to be subquadratic. So in general, if there are n different shares, this is always going to happen, right? So a key learning over here is, the number of shares should be smaller than n. So maybe the number of shares, we split the message into some kappa number of shares, and then ensure that this is in the reshare phase, it is reshared with sufficiently many parties. In particular, there's at least some honest party who would be resharing it for us. One approach to actually achieving this is to use a kappa-sized committee for resharing each share. Okay, the intuition behind a kappa-sized committee is the following: you want some honest party to reshare a share, and if you elect a kappa-sized committee, hopefully one of these parties is going to be honest, and the reshare will be successful. But while this is one of the approaches that we thought of, it turns out that it actually does not do the job for us. In particular, it actually just does not achieve the communication complexity goal that we sought after. Right. So if you're thinking of kappa parties sending to n messages of size L over kappa, that in itself for each share incurs NL communication. And if you extend it to kappa shares, your communication complexity has blown up by a factor of kappa than what we are looking for. Moreover, it's unclear as to how these committees are formed and how do we distribute these shares with the kappa different committees, because in the sharing phase we do not know who these committee members are. Otherwise, an adaptive adversary would just corrupt all of these committee members. It turns out that we can address both of these questions or challenges in a rather clean fashion. And here's exactly what we do in our approach. We publicly split all of the parties into kappa different buckets, each of size n over kappa. So in this grid over here, the grid represents all of the n parties. Each of these rows represent kappa different buckets, B1 to B kappa, and each bucket has size n over kappa. In the distribute phase, we require share I to be shared with parties in bucket I. Okay, so we're splitting the message into kappa different shares, S1 to S kappa, and each share I, Si, is being shared with all parties in bucket Bi. In the reshare phase, we elect a single, note that we elect just one committee of size order kappa, and these committee members would reshare the shares that they have received with everyone else. So in particular, if I'm a party in bucket I, and I'm also in this order kappa sized committee, then I would engage in the reshare step for share Si. Okay, so in the graphic over here, we're representing all of the committee members in squares, honest parties in black squares, and Byzantine parties in dotted red squares. So first, let us convince ourselves that the solution actually gives us better communication complexity. So if you're looking at the distribute phase in particular, then you have a set of parties who are distributing, and this can be bounded to order kappa. So you have order kappa parties sharing L over kappa size shares to N over kappa parties for a given share. And that by itself will incur Ln over kappa bits per share. And if we do this for kappa different shares, it will incur a communication complexity of order Ln bits. So we're good there. In the reshare phase, you have just a single committee of size order kappa, and they are sharing an L over kappa sized message to all N parties. So that would incur a communication complexity of Ln bits. So that's good too. But if you're thinking through this, then you may think of, hey, are there potential concerns over here? In particular, we are electing one committee of size order kappa, which means each bucket I has in expectation only order 1 parties who can reshare I. And there may be, because of the stochasticity, there may be buckets which have no honest parties, and there may be buckets which have only Byzantine members in them. And moreover, if you're thinking of this from the perspective of the adversary can actually perhaps adaptively corrupt parties in different public buckets so that not enough shares are reshared. So if you're thinking of this from the adversary standpoint, observe that for any bucket, if some honest party reshares a message, then all honest parties are satisfied. That's no good for the adversary. But what the adversary is trying to maximize is the total number of buckets where there exists no honest parties who can perform this reshare step. It turns out that we actually address these concerns using a very subtle analysis of a balls and bins analysis using McD-Armid's inequality. So the balls and bins analysis essentially says that if you throw C kappa balls, referring to these committee members, into kappa bins in such a way that a minority of them can be corrupt, then our goal is to ensure that there exists some constant C such that you have sufficiently many buckets or members in sufficiently many buckets that are honest, and these members can perform the necessary reshare step. And I invite you to take a look at our work to understand these details. So I must also mention that I'm glossing a lot of other details and other subtleties in the protocol over here. As an example, when you're performing this distribute step, there are these committees that are performing these distribute step, and you want to ensure that the committee, so when you're agreeing upon these messages in a BA protocol, you're agreeing upon one of the inputs, right? So if a committee is sending these messages to everyone, you want to ensure that at least one committee member knows or has access to the message who is to distribute in the first place. So there are subtleties involved with how different sub protocols are invoked and so on. And again, for those aspects, I invite you to look at our work. So let me conclude by presenting the key result that we achieve. So we say that for any epsilon greater than 0, we show that there exists an adaptively secure BA protocol achieving a communication complexity of NL plus N poly kappa for L bit inputs. And we show it under two different conditions. Under a synchronous network, we can show that we can tolerate a minority corruption. And under an asynchronous network, we can show that we can tolerate an N over 3 corruption. So there's an epsilon slack over here, which we get because of the sampling process. And note that all through the talk, I never spoke about the network condition, synchronous or asynchronous, partly because all of these complexities related to synchrony or asynchrony is kind of absorbed by the underlying BA protocol. And it does not really affect the core content of the core ideas of that we are presenting over here. So with that, I'd be happy to take questions, and here's a link to a paper. Thank you.
Thanks for the talk, Karthik. Are there questions? Okay, I have a question. So, I mean, a fairly minor one. I'm curious where the poly K comes from. Is it from your combinatorial analysis, or is it some sort of cryptography that's hiding there?
That's a good question. So under asynchrony, there is cryptography hidden over there. So it basically comes from the underlying BA protocol. The state of the art for asynchrony is the poly is actually kappa to the 6. For synchrony, it comes from the actual poly is kappa cubed. And I think it comes from the size of the message, because we're talking about the number of bits. So if you're sending VRF values, so that's kappa bits, as well as the number of rounds of communication. So it's kappa people sending kappa sized messages. I believe for kappa rounds or not, but I think so those are the two kappas. I don't remember off the top of my head what the third is.
In terms of cryptographic assumptions, you presented your work as like combining two different approaches. Are the assumptions that you use basically just a combination of those two, or is there something new in this?
It kind of comes in from the underlying BA protocol. So in the case of synchrony, you would use whatever setup assumption is required for a VRF. Under asynchrony, I think the best underlying BA protocol requires a lot of other assumptions. So, but everything comes from underneath. We're not introducing anything more.
Yeah. Thanks for the answers and thanks for the talk.
Thank you so much.
Yeah. And that wraps up this session. Let's thank Karthik again. Now break.
This is bound to happen at some point. And like Mr. Edward Hawk tested positive, and he kindly let us disclose his name. So if you were in close contact with him, please take a rapid test. I mean, you do not need to do anything else right now. I mean, so the person who tests positive is basically confined for 5 days. But if you have contact with him, you do not need to do anything more than what you are doing now. You should take a test today and do a test every 2 days after that, just like we announced during the information email. So if you need any tests, please come to the registration desk and get yourself tested, and kindly inform us if you are positive, of course, and try not to get into contact with more people. Otherwise, I mean, sorry to bring this news, but I mean, it's a commonplace happenstance nowadays. So, you know, we try to continue with the conference. Thanks, everybody. Okay, I mean.